and I are going to do something to this class. Before I start, for the benefit of the participants there is this thing which I want to state. I had trouble drawing that flower neatly there. So I asked some of these kids to draw the flower for me. Immediately, some of them, they picked up their bag, they held it this way, so that you get that, yeah. She just held it this way, she got this, and then she put the thing up and she drew the flower. The flower there was done by these set of ingenious kids. Okay, so there were some kids around here who could do that flower. Will you all try to draw that flower? You can use the round. Is there somebody who has not drawn this flower? I was told that some of you draw these flowers at school. Is there somebody who has not done this? Do you know how they drew? Yes. You know? Draw it? You don't have a rounder. Maybe you can share it. Huh? Without rounder also you can share. You use the rounder? Okay. Can you use that rounder to? Okay. I don't have that. Can you do it on the board? On the board. Take some. Yes, you can, teacher. Is the topper? Anand is trying to do that without a rounder. Huh? don't know how to do. Okay. Done? Drawing, just watch what he is doing. It's a little difficult to see because the circle which he has is small.
Because it's very hard to hold that.
Or can you make an laser copy of something? No? Why? Huh? Why? You will learn to make it stronger. Yeah, there is it's not good enough. You can do it big as well. Can some of you try doing this without the router if you have some manual kind of thing with you? Can you try doing it without the router? No, you don't have to do it. That is better. What were you trying to do? Okay, do this because we have a very, with the angle it's not possible to do on the board. He has made 2 petals, but I want you to try and do this. Okay, with just a circular thing without using your rounder. Okay, you have to tell me how you are doing it without the rounder. Now, most of you I saw have made a flower. How many petals does your flower have? 6. I saw a 7 somewhere.
Someone said 8.
No, I saw a 7 somewhere.
8? No.
Those of you who did with the rounder, you got 6 petals. Now, done? I'll come back to that as to how you did that. Okay, now those how did you? Those of you who did it with the rounder, how did you do it? Whoever, one of you, yeah, tell me.
Teacher, first we have to draw a circle and then we have to keep a rounder on the circle.
Can you show it there with the rounder? With the rounder. Don't press hard on the board, but just show me how you did. No bend. Okay, so what he is saying is, he first drew a circle and then he put the pointed this thing of the compass here, and without changing the radius, he drew one arc. Then wherever this arc cuts, he put the compass point there again and drew the arc. And how many times did you do that? 6 times? Okay. And once you did it 6 times, you had a flower. Are you sure that if you do this every time you will end up with a flower? Yes. Huh? Why? Why? Huh? You did with the barrel. Okay. How? I will come to that at the end of the. Are you sure that every time you do this, you will end up with a flower? Huh? Why? If you don't go wrong. Okay. Why? Huh?
If we use the same procedure, then we can get the flower. Because the arcs are, when we draw one arc, the same distance is there. And again, we divide it from the point where we had taken to draw the arc. On that point, we draw again a arc, and from so it comes again on the point, and it's a semicircular which from the flower.
I am not convinced that that will happen. Can you prove to me? Yeah.
Ma'am, first we should draw a circle, and after that one point we should keep one point of the runner we should keep on the circumference, and the other point on the radius. Then afterwards draw an arc, and then we should connect the end point of another end point of the other end of the arc, and again draw an arc. So in this way we will get 6 points.
But how can I convince myself that every time I do this, I'll get that flower? One way of looking at it is there are 50 students here, every one of you did that, and every one of you got a flower. Right? Right? So, I conclude that whenever I do this, I'll get a flower. I can do that? Huh? Just because a group of 50 students tried and I saw that they got a flower, I assume that whoever draws it in any corner of the world at any point of time, they will get that flower. Can I assume that? Yes. Yes? Okay, I will give you another example. Let's leave the flower for a minute. I have this relation here. X square is greater than x. Am I correct in writing it? Yes. Yes. Can you convince me that it is correct? Yeah.
And x square is x into x, and single x is only x. So
That's what I have written there. X into x is always greater than x. That's what I have written there. Huh? Huh? Yeah.
X is 1, 1 squared is also 1.
Okay. Okay, let me put it as greater than or equal to then. You are saying that if I take x is equal to 1, then 1 square is equal to 1. If I take x as 2,
Then it's greater.
so So it's fine. 2 square is 4, which is greater than 2. If I take x equal to 3, 3 square is greater than 3. Yeah.
But if we take 1 by 2, then it is
Okay.
so
I could have tried to convince myself of the proof by keeping on putting values 1, 2, 3, 4, 5 and so on. Okay, so I put values up to 100 or million or whatever it is. Whatever value I put, I am finding that that thing is holding true. So I make an assumption that it is true. This method of proof is what we use in science. You observe something and you see that something happens over and over 100 times, 1,000 times or whatever. So you assume that that's true for the that's true always. Another example would be you know that human beings have got their heart on the left, right? Can you prove that statement to me that human beings have their heart on their left? Yeah, how do you prove it?
And put your hand on the left side and if we run for or do any hard exercise.
So all of you put your hand on your heart. Where is your heart?
Left hand side in the
Everyone?
Okay, so from that, how can I say that every human being on earth has
Yeah,
got?
so you want to conclude from that every human being has a heart on the left.
because when they open the human
For on all the surgeries that have been performed, or maybe on most of the surgeries that they have performed so far, they found that the heart was on the left. Fine, that is one piece of evidence. You are saying that you put your hand on your left and you hear that tuck tuck. Okay, so which means that you all have your heart on the left. But can you say for sure that every human being on earth?
Because some of them have it on.
There are people who have it on their right. 1 in 16,000 people have their heart on the right. So till such time you find, till such time you look at the sample of people, large enough sample, you could take 1,000, 2,000 or whatever, and if in all of them they have their heart on the left, you conclude that till I find further evidence, I will hold the belief that every human being has got a heart on the left. So this is a method of proof that science adopts in proving something. Proving something means what? If you make a statement, you have to give evidence. Bhagesh was saying, whatever statement you make, you have to prove that. You have to give me evidence. If you don't give me evidence, I am not going to take that. So if I were to make a claim that every human being has got his heart on the left, what is the kind of evidence that I can give to convince you? I will come and tell you that, okay, I called 3,000 people from all over the world. I found out where their heart is, and if every single one of them, they have the heart on the left. So this is evidence enough to conclude that every human being has their heart on the left. Now, after that, if I come across somebody who has got their heart on the right, then I will have to go and correct my this thing. So till such time, till such time that I have further evidence, I will conclude that every human being has their heart on the. So this is a scientific way of reasoning, which is somewhat similar to what we did here. When we said x square is greater than x, we put in values 1, 2, 3, 4. It was working for all those numbers. So till such time she came up with the value of, if I put in a half here, half into half is not greater than half, we can hold the belief. If in our world fractions don't exist, till such time you come up with the counter example, I will believe that that particular thing is true. Now in a similar way, you are telling me that 30 people in this room drew, and for them you got all the, for all of you, you got a neatly formed flower. Based on that, can I conclude that at any point in time, if any person does that, you will get that flower? No. So what is needed to convince me that it will work?
It will always work,
It
whether
will
it's
always
the size
work.
of the solar system or anything.
Yeah.
Or less than 1 millimeter.
Huh?
Or less than
Less than 1 millimeter, this result doesn't hold.
Yeah. Ada. He says that if it is less than 1 millimeter, it doesn't hold. So,
Can you disprove that statement?
prove that? That even if you take your circle with radius less than 1 millimeter, it will hold. More claims that it will not. So, can you convince him that it will hold? Yeah, you were saying something.
No, because you don't have instruments to do that, but if you can hypothetically imagine it, then it is possible.
What is this hypothetically?
If you can just imagine the situation in your mind.
I can't imagine the situation.
So
You have to
so
reason
you
it out.
can imagine unicorns, so unicorns exist.
Yeah.
No, but
Yeah. Let me reformulate the question a little bit. Okay, you did this, right? You had this as a circle and you drew. Then you put your compass here and with the same radius you drew, you got an arc here. Then you put it here, you got it here. Put it here, you got it here. Put it here, you got it here. Now put it here, you got it here, here and here. If you put this, it's so neatly fit in with the scheme of things and again it came there. How can you be sure that this will always come
It's
there?
surprising, right?
That it fits in so neatly. So, yeah.
We are keeping the radius same only, and the point which we are taking on the point means if we take the point, we need to take here, we are drawing. So if we put it here and we keep the point similar and we take it from here, it comes again on the point. The distance is remaining same, so that's why it's coming like that.
But why should it come to the same point after the fifth arc? Yeah.
because I wake up and I see my table beside my bed. Then again tomorrow I wake up and I again see the same table and it's not surprising. The same way, everything is same and therefore the result is same.
Okay, day after tomorrow, your mother removes the table and
If that happens here also, instead of taking the same radius, I am taking a bigger radius. Therefore, I will see a change. Same way.
But how do you know
But
that?
how do you know
how
that?
do you say if it's less than a millimeter, it will behave the same way?
even with this, is it not something mysterious happening here? You do that when you were doing it. In the last this thing, it's so neatly coming and fitting in here. It could have been otherwise. It could have ended up here or here, but that's not happening. It's perfectly going to that same point. Yeah.
There is no external force, why will it change?
Where is force coming in?
This is drawing.
No change. Then it will remain same.
With that same radius, when you were drawing it, you drew it 4 times, right? All these things you said the distance. You said that this is the radius that I want. But in the last case, you found that that is what is remaining there. That need not be, it could have been something else. You didn't change, but the mark that you made, why should it coincide with the earlier mark? It could have been less or more. Why? Yeah. What is the reason? That's what we asked you.
What we are saying is that sometimes it goes here, sometimes it goes here, sometimes it goes here, sometimes
It could be. It could be. Yeah.
While drawing hexagons, we draw it in the circle because we get 6 arcs at equal distance. So using the similar property, this is possible.
Okay, so you are going to use the property of the hexagon and do something. Essentially, you have to give me a convincing argument that whatever it is that you will do, you will get that point coinciding with wherever you started. You use your property of hexagon. Essentially, now what we are asking you to do is to prove it mathematically. In science, we said if you look at 10,000 people and if they all have a property, we will say that if we take, we will say that the entire population has that property. Which means if we take a large enough sample, if we take a large enough sample and if that sample has got a property, we kind of extrapolate and say that the population has that thing. Here, but there can be exceptions, you know, which you can come up with. So can you give me a foolproof argument to show that that sort of a thing will not happen here? Yeah, let me hear you out first.
Now we join all these points together.
Yeah.
Which point?
Mother. Huh.
These?
Yes.
So you want me to join to this?
No. Without adjustment. So now this again is same. And the side of the hexagon does not miraculously change.
You can have a hexagon. 5 of whose sides are the same and the 6
And one is different. Or 4 are the same and 2 are different.
All hexagons in the world are not regular hexagons. Yeah.
When we draw any circle, the measure of the middle angle is always 360. It never changes.
Okay.
And so that is where we are getting the 6 petals of a flower.
How
Lots
do
of
you
steps.
given that?
If we just try to measure the, if we make a hexagon inside way smaller, which is inside.
You want to come?
If the point does not come
Let's see what she has to say. One at a time. Yeah. How are you going to convince me? Turning that way is not going to convince me. Think about it. Huh?
In the morning you told me triangles can't have curves.
Let's take it out. So
Yeah, now it curves.
if we measure the angles of each of this, it will come up with 6
Of each of what?
Maybe you can draw your this thing a little larger so that.
These are curved lines. I don't know what it means to say take the angle of it. Ah.
And as the same and put the then
Listen to what she has to say.
We don't know. That's what we are asking you to do.
You can't make wild claims like that. We won't believe you.
Yeah.
You have to give us evidence.
Give us reasons to believe what you're saying.
Think about it. There is a hand there. There was a hand there. Yeah. You had put up your hand. No? Okay. Ah.
So, what I was thinking is, we join the center point with all of the points on the other side. These are all radiuses, all of these should be combined.
We draw that separately now. The triangle.
So just let's pull out just.
Or we could just erase that flower there.
That's simply.
So, we can, we know that these three sides are all the sides are equal. And because what is the opposite angle, all the angles are also equal.
No, you get this angle by vertically opposite. You get this angle equals this angle, this angle equals this angle, and this angle equals this angle. But not that all are equal.
So then we can do like these two triangles as well. So, I mean, we can get that these two triangles are equal.
Okay, you can put one on top of the other.
Yeah, and so But for this, and if you know that the measure of an arc equals the angle inside.
I don't know
What do you mean by measure of an
what
arc?
do you mean by measure?
And easy.
The length of this arc
Yeah.
is just going to be equal to the angle inside it.
How is the length be equal to angle? So the length is one right angle.
Yeah.
How can
You had something.
How would you do that?
Speak through the mic. Speak through the mic.
This angle is equal to this angle.
I mean, this angle is equal to this.
Yes. Then this angle is equal to this angle.
Yeah.
And this angle is equal to this. And now, this angle.
Are you assuming something?
That is straight line. This or the sum of all the angles are equal to this angles. So therefore, all angles are equal.
No, not necessarily. This angle is equal to this angle, this angle is equal to this angle, and this angle is equal to this angle, but they are not connected. How do you know?
Because we are making the same way.
So how did you draw this? So you put your the compass.
Here and we draw the arc.
So
It is the same.
so did everyone see what she said?
You have to use the mic.
You have to use the mic.
So, as this is the radius and we took the same and we drew the arc here. So this is from the equilateral triangle and so it is 60 degrees.
So did you guys hear that? So what she said was that this is the radius of the big circle. Everyone agrees? Yes. Yeah. And how did we get this line? Yeah. And how did we get the arc, that original arc which was here? We put the compass thing here, and we, with the same radius, we drew it like this, right? So this is the radii, these two are the radii of this circle. Does everyone see that? Yes. Yeah? So that means this is equal to this, because the radius of a circle, all the radii are the same length? Yes. So since this is equal to this, and this is equal to this, then all three have to be equal? Yes. Yeah? So that means this is the equilateral triangle. Right? Yes. Now what do you do?
So in the equilateral triangle, the angle is 60 degrees.
We don't like that degree stuff.
Okay, so there is some angle and similarly this triangle.
How many right angles are?
Or how much of a total complete circle is it? Or complete rotation?
2/3 of a right angle.
So 2/3
or you
of it.
could say
Once.
what part of a full rotation? What part of a 1/6?
Let's call this 1/6. So would the same be true for this?
Yes, because this are also sides are equal and this is also equal. And this is also the same.
Yeah.
You can't hear what she's saying.
Similarly, all are like that.
So say it again.
So similarly, all the triangles are equilateral and have the same.
All the triangles, no. Our question was, after you've drawn 5, how do you know the 6th one can be drawn? So we don't have that 6th one right now.
So as we go on, we
So we drew the second one, and that's 1/6.
similarly here.
So this would be 1/6. Now what's left?
Now if we add it, it is 4/6. So 2/6 of the part is left.
Yeah.
So we can say that the remaining is 2/6.
Yeah. And so where did you start? You started from?
Yeah.
Yeah. Okay. So you drew this, then you started from here, you drew this up. That means we have this is equal to this is equal to this. Right? This is equal to and so what are you left with? 1/6. 1/6?
Yes.
So, and 1/6 would be what? The same, you could copy paste the same triangle?
Yes.
And with that the same remainder arc. Right? If you had this drawing, put it there. Right? Did everyone see the argument?
Yes.
You sure?
Yes.
Okay.
You should spell it out.
Huh?
Just go through the argument.
Go through it once? Okay. So what you did was you drew a circle with some radius. Right? Now you picked a point.
Madhav is going to spell out the
Go through
argument.
the argument.
Your task now is, Madhav is making a lot of assumptions in between. Okay, just find out what assumptions he is making.
Okay? So you pick a point here and you draw a circle with the same radius. Right? So now join this to this. These are both equilateral triangles. Right? You got why does that happen? Somebody else.
Yeah. There's a hand that's going up there. Yeah.
So the radius of this is the same as the radius of the original. So that means, and all radii are the same length. So we can do this. Now you put your compass. How did you do the next part? You put your compass here, and you put the other end here, and you drew another arc, something like this. No. How do you do it? It goes through the second. Right, something like that. So now, once again, you join this here and you join this here, and by the same reasoning, this is equal. Now, you put arc here, you draw this here, and you extend, and by the same, this is equal. Because we've drawn 1, 2, 3, 4. And now you put it here, you draw an arc here, and it doesn't really look it, but that's equilateral. And what you're left, so now, but since these are equilateral, that means this is 1/6, this is 1/6, this is 1/6, this is 1/6, and this is 1/6, and what's remaining? Right? So now what can we do? We can pick this up and copy this there.
Can you do it?
Can we?
Yes.
Why?
Yes.
Because this would fit in. There would be this prime, and it would end in because the radius is the same thing. So what are the assumptions I made? Jashri said I made assumptions. I don't know what assumptions I made.
You're using the same radius.
That's from the procedure. The procedure told us that.
You assume.
The procedure originally told us that, right? So we didn't assume that.
Yeah. The midpoint.
What about the midpoint?
You assume where the midpoint was.
No, we drew it. We started from here. So we know where the midpoint is. Yeah.
The points from which we drew the arc.
But we picked a random place first to start with. Then we know where to go next. Yeah.
The angle.
What about the angle?
We took it that it's equilateral angle, so we assumed it at 1/6.
Okay.
Did we assume that or did we? So how did we get 1/6?
Because the property of equilateral.
So Have what? What is the property?
Equal sides.
What does equilateral mean? How do you define an equilateral triangle?
A
A
triangle
triangle, all its angles are equal.
sides and
Sides and angles are equal.
yes.
Do you have to say both?
No.
What do you have? What does equilateral mean?
What does lateral, equilateral mean like?
Huh? Sides. Equilateral means all sides are equal.
Okay, so that is the assumption, the big assumption we've made. Equilateral triangles have all angles equal. Because equilateral means all sides are equal, right? From that, we're going to all angles are equal. When you do that in a quadrilateral, here all sides are equal, but all angles are not necessarily equal, right? So why is it true in this case?
One more assumption which I want to point out. This particular angle Madhav said was 1/6. And just because this angle is 1/6, he assumed that this triangle is equilateral. He just told you that this can be cut and paste there. I don't see how you can cut and paste there, Madhav. This is the triangle that you have, right? You have a triangle.
It's
You
obvious,
have
isn't
this
it?
angle to be 1/6, and you are telling me that you can cut and paste. I don't see how.
Because the two sides. Because the two sides and the included angle is
Huh?
the two sides and the included angle is same.
Which is the two sides and included angle the same?
The two sides.
Okay. Okay. Can you're saying that if I look at this triangle and this triangle, these two are the radii. Here also I have these two the radii, and the included angle is the same. Therefore the
And if you join these two, then this will equal to this. We already know this is 1/6. So that part you proved. That part is still left.
So now, if you prove that, if somebody tells you that if I have a circle with radius less than 0.5 millimeter, or if somebody says that I'm going to take a circle as large as the solar system, can you convince them that still this will work?
But only if you prove that. Yeah.
We can prove it if we can prove it by cutting actually those sides. The angles we can just cut it, and if we put it then it will form 180 degrees. So and at the sides are equal, then it will be 60 degrees.
How do I cut that?
If we draw it on a paper,
But then that's not that one.
Now, is that a mathematical proof? If you cut that and put it in a paper, you will cut 10 triangles, you will cut 100 triangles. In all that, you will see that happening. So, will you be convinced of that? That in any triangle that you draw, this will hold.
How do you know it's even true of this one? We're not going to cut the board.
But we can simply measure.
Yeah? Okay, let's leave it here. You guys can suffer a bit.